Hello, once again, I'm Mr. Steele, and I'm here to kind of substitute in and offer a little bit of insight into the world of trig identities. If you're watching this video, odds are you watched yesterday's video first, which overviewed all of the fundamental identities, basically the building blocks upon which all of our work in this unit is going to, build. The truth is, though, although we went through and kind of proved a bunch of identities and talked about how they might be useful and gave you some context for them, we didn't really do much with them. So in this video, I'm going to go through the process of actually applying those fundamental identities and simplifying trigonometric expressions. So what you're going to see are some really crunchy looking expressions that are just packed with trig identities. And your job will be to decide which trig identity to apply and which one to use, and then to try to simplify and clean up that expression into a form that's just simpler, has less trig expression in there. We want to kind of get to the heart of what's there. There will be moments where it'll be ambiguous whether or not we've done enough or if we are ending in the quote-unquote right spot, but that's okay. Our goal here is to just get used to looking at the expressions we're going to see and applying the trig identities that we're going to look at. In this video, as I go through, I believe I have 6 examples. I might be miscounting by 1, but I believe I have 6 examples. I'm going to work through each one. I'll talk about the identities I see and call back to them by their name. So we'll talk about reciprocal and cofunction and Pythagorean identities. And when appropriate, I'll show you multiple strategies for attacking a particular identity or a particular expression. Because the truth is, although I might see a Pythagorean identity, you might instead see a bunch of reciprocal identities, and we'll get to the same place eventually. Like one path just might be a little smoother than the other. So it's completely up to you which way you want to go, as long as you apply valid identities every single time. So each instruction in this video, it's all going to be basically examples and kind of insight and strategy that we'll be talking about. But as the instructions say on this first example right here, use identities to simplify each expression. So we're going to have to look at stuff, recognize structures that we saw in that identities video from before, and then actually start to attack the expressions that we see. So let's jump in and take a look at the first one, which looks like an Oreo right now. There we go. So our first expression is sine of theta plus cotangent of theta times cosine of theta. And our goal here ultimately is to somehow break this down so that it's a much cleaner expression. Now I'm not sure off the top of my head what it's going to look like. I could look over at my notes that I took earlier, but we're just going to look at this and try to see if we can pick out some identities. So when I look in here, I see the presence of sines and cosines first. Sine and cosine aren't exactly the building blocks of every trig function or ratio or identity, but the truth is they kind of are, right? Sine and cosine are the first two that we learned. They're the first two in SOHCAHTOA. Tangent is sine over cosine, and then the other 3 are either reciprocals of that or reciprocals of literally sine and cosine. So my thought here is I want to try to get everything to look like sine and cosine, not the least of which because I'm probably much more comfortable with sines and cosines anyway. So here's my thought. When I look at this expression, I see sine, something that isn't sine or cosine, and then cosine. So I'm going to focus my attention right now on the cotangent of theta. In fact, what I'm going to do is I'm going to take that exact expression that we have here. Let's see if I can do this right. I'm going to take that expression, and I'm going to replace cotangent with an identity that involves both cosine and sine. Specifically, I'm going to involve cosine of theta over sine of theta. In other words, what I'm using here is a quotient identity. So I'm pulling a quotient identity in so that I can convert cotangent to cosine over sine. Now that I've done that, I haven't really accomplished a whole lot, right? Nothing's undone itself, nothing's like divided out. But what I'm thinking here is that if I take one more move forward, I can look at this expression as sine of theta plus cosine squared of theta divided by sine of theta. Now that move itself is just the same way, kind of hasn't done much except cleaned up the numerator on that second fraction. But what I notice is that I've got a denominator on the right side, but not on the left side. And God, I feel like the left side's going to feel left out if I don't do something about it. So what I'm going to do next is kind of a common strategy from just arithmetic. I'm going to get a common denominator and just make sure they both have the same denominator, because then maybe we can kind of crunch it together into a single trig expression. So over on the left side, I'm going to multiply by sine of theta over sine of theta. So when I do, of course, the right side of the equation is going to stay exactly the same. Nothing has changed right there. On the left, though, in our denominator, of course, it's going to be over sine. That was our goal, so seeing that sign down there is a good sign. And then in our numerator, we're going to have no longer just sine, but sine squared of theta. Now looking at this expression, like, here actually I should probably write this in there. What do? We did common denominator. It's not really a trig identity, it's just kind of a thing that we do when we're adding or subtracting fractions. So now from here though, what I notice is that both of these fractions, these rational expressions we have, sine squared over sine plus cosine squared over sine, they have the same denominator. And remember, our whole goal was to get a common denominator so we could kind of condense it into a single expression. So the next move I'm going to make is just to kind of use properties of common denominators to rewrite this as the single expression, sine squared plus cosine squared, all divided by sine of theta. Now, in looking at this expression, again, it just looks like we've kind of brought everything together, except this is one of those powerful moments where hopefully you're seeing what I'm seeing. There's something really nice that just happened here. What is sine squared plus cosine squared? Well, the truth is, hopefully you learned from yesterday, that is one of our most fundamental identities. It's the Pythagorean identity. And in fact, sine squared plus cosine squared is equal to 1. So right here, we can rewrite this expression as 1 over sine of theta, using like the single most fundamental Pythagorean identity. And I'm going to write it as Pythagorean ID. If you're taking AP Psych, this is not Pythagorean ID. Like, that'd be super ego. Now I can't make a joke, whatever. So we have 1 over sine of theta, and of course that's not a bad ending place. We've condensed and gotten rid of a lot of expressions, but 1 over sine of theta is an expression that I recognize. That is equal to cosecant of theta. And so I did that by using the reciprocal identity. So this first expression we had didn't look like it was all that involved, but we actually got to use, I think, 3 separate identities, and we were eventually able to condense it to simply being equal to cosecant of theta. So that is the sort of process here. Obviously, I'm moving slowly and talking about each identity, trying to give you some insight into what's going through my brain as I do it, but at the same time, we're just applying these relationships that we already established and kind of proved yesterday even. So there's our first one. That first expression, sine plus cotangent times cosine, is actually the same thing as cosecant of theta. Kind of a neat observation, kind of a neat result, I would say. The next one we're going to look at, I think, is a little bit easier to navigate, or at least to know which identities to apply, because it does what I'll call telegraph. It telegraphs what type of identities to use because there's certain structural elements that just kind of scream for a particular identity. In particular, what I notice here in this expression, which is, by the way, cotangent of pi over 2 minus theta times cosine of negative theta, I notice that in the first expression, the cotangent portion, we have pi over 2 minus theta. That immediately speaks to me and says cofunction. I was trying to do a voice, like a voice that would speak to me. Cofunction. That's kind of creepy, I apologize. But we seem to have a cofunction identity. The presence of pi over 2 minus theta, or 90 degrees minus theta, tells us that we've got a cofunction relationship. So we'll apply that in a second. Likewise, when I look over on the right side, I see cosine of negative theta, and that negative theta is what screams to me that we have an even or odd identity. So in fact, in this problem, I would say this one's probably a little easier than the first one, just because it kind of tells us much more directly what to do. That said, the identities are less memorable maybe, so maybe it's a little bit more challenging. Having said that, let's use those identities that we know. First and foremost, we talked about the cofunction identities yesterday as being pretty memorable simply because the cofunctions go with their other name. So for instance, sine of pi over 2 minus theta is cosine, or cosecant of pi over 2 minus theta is secant. Well, in this case, we have cotangent of pi over 2 minus theta, which should be equal to its naming pair, tangent, but of theta. So I'm going to replace or rewrite that first part of the expression, the light blue version, as tangent of theta. Then I'm going to multiply that whatever the cosine of negative theta is equal to. Well, moving over to that even-odd identity, with cosine of negative theta, cosine was the only even function that was in there. And again, it was a small thing, but remember if we started here with our angle theta and x, y, and r, that negative theta would be the angle right below it. And for this, even though the y value or the opposite side would be opposite signed, the truth is cosine is still adjacent over hypotenuse, which means it's the exact same value. So cosine of negative theta is actually just equal to cosine of theta. So I can go ahead and make that substitution in here on the right as well. Having done that, we now have tangent of theta times cosine of theta, which is pretty great, but I don't think it's necessarily going to finish the problem for us, because tangent cosine isn't something by itself that I recognize. But taking that same strategy from the first problem in here, tangent of theta could be transformed into sines and cosines. So in fact, that's what I'm going to actually aim for. I'm going to rewrite tangent of theta. Oh, here, I'll do it this way. I like taking these colors and doing it this way. I'm going to go ahead and replace tangent of theta with the expression sine of theta over cosine of theta. In other words, what I'm using is another quotient identity. And again, those quotient identities work really well to take something that doesn't have sines and cosines and to kind of represent it in terms of sines and cosines. Having done that, this is actually a huge victory for us. Now the cosine and cosine will divide out, and that leaves us with simply sine of theta. So right there, we find out that that kind of crunchy expression up there that had two awkward arguments, pi over 2 minus theta and negative theta, just cleans right up and resolves into the beautiful, harmonious sine of theta. So once again here, in this case, I'd say this problem kind of leads us in a particular direction, so follow the path if there's one that's there. If you see a negative theta, think even odd, and if you see that pi over 2 or 90 minus theta, immediately jump straight in with a cofunction and see if that doesn't clean things up. The next one we're going to hit, well, this is example C. We're doing the same thing. We're still going to be using identities, but in this case, as I look, there's not a single identity that kind of jumps out at me. I mean, don't get me wrong, if you see secant, it'd be very reasonable for you to think to yourself that maybe a reciprocal identity would be valuable. Maybe this would be an opportunity to bring in 1 over cosine. And I'm not going to disagree with you. That's definitely a valid strategy. The problem is, if we switch to 1 over cosine, imagine what those denominators are going to look like. We'd have 1 over cosine of theta plus 1, and something similar on the right side, and that's just a complicated denominator. That's like if you need to reach something on the ceiling or something. Maybe you're painting and you want to have to reach the ceiling, and you stack a couple textbooks and a frozen turkey on there, and you try to climb on top. It's just, it might work, it might be fine, but it just doesn't seem like the safest and cleanest way to approach the problem. Maybe get a ladder. Who am I to say? Having said that, what I'm thinking here is that this is a situation where we are just subtracting two different fractions. So instead, what I'm going to try is something that I would use for much cleaner fractions. I'm going to attempt once again to just do a regular arithmetic move. I'm going to multiply up and down to get common denominators. So over on the left side, actually let me give myself a little bit more space. I just want to make sure I can write this nicely. On the left side, I'm going to multiply up and down by secant of theta minus 1, the denominator that I see over on the right side. So if I multiply up and down by secant of theta minus 1, of course, we'll be able to change the expression on the left side. On the right side, and I should probably add one more thing. I shouldn't be cavalier with parentheses. We should think of that denominator as being a factor in itself, too. It'll be necessary for us to do that. On the right side, I'm going to make a similar move. I'm going to, again, treat the denominator as entire factor. Well, we've got the secant of theta minus 1 down there. If we want to get a common denominator, we now need the plus version. So I'm going to multiply up and down by secant of theta plus 1. So I'll do exactly the same kind of operation, just with a slightly different denominator. Having done that, of course, this looks awful. We're totally making this expression look worse. But sometimes, it's always darkest before the dawn. I think that's from an action movie of some kind. Apologies if I'm misquoting it. But the idea is we've made it worse so that hopefully we can resolve things a little bit. So as I look at this expression, the biggest thing I'm going to do is I'm going to recognize that our denominator at least is the same across the entire expression. So I'm going to go there first. Both the left and the right fractions will have secant of theta minus 1 times secant of theta plus 1. And I should be using proper colors. I apologize. That's why I have the color buttons up there. So we're going to have secant of theta minus 1 and then times the plum version, secant of theta plus 1. Now in our numerator, we've just got a bunch of things being multiplied times 1. So in this case, we don't have to worry too much about stretching things out. At least on the left side, we're just going to have secant of theta minus 1. Now on the right, we do have this minus sign in there. So although I said we don't have to do a whole lot of work here, it would be a poor choice if we just distributed this plus and then tried to deal with the minus sign later. Let's instead take an old trick that I learned from Miss Nakamura, which is change that to a plus and make the numerator negative. So now we're going to distribute that negative sign in there. When we do, we're going to get negative secant of theta and then minus 1. So there is our new expression. Still not exactly a winner, but let's take care of what we can. So in the spirit of taking care of little arithmetic things, look at our numerator now. We have secant of theta minus 1 minus secant of theta minus 1. Well, I notice secant of theta minus secant of theta just zeroes out, which means this expression is going to give us a negative 1 minus 1, or negative 2 in the numerator. So that's pretty nice. We've gotten rid of all the trig completely. Sure, there are some of you who just hate right triangle trigonometry who are like, yes, no trig. Well, hate to disappoint you, the rest of this lesson's trig identities, but that's okay. Now in our denominator, like this is a little bit different, but in our denominator, we have secant of theta minus 1 times secant of theta plus 1. What I notice is not a trig identity yet. I notice a difference of squares. I recognize that a squared minus b squared kind of structure. So in fact, I'm going to go ahead and apply that. If we multiply this out or apply difference of squares, we're going to get secant squared of theta minus 1 squared, which is of course the same thing as secant squared of theta minus 1. So there is our new version of the identity. Now some of you might be tempted to just kind of call it a day right there, but I think that there's more that we can do here. In fact, I'm confident there is, not just because I have all the work that I did earlier right over here. Instead, what I want to point out is that denominator there, secant squared minus 1, reminds me of the Pythagorean identities. So depending on how you learn those Pythagorean identities, like you may or may not have one off the on the tip of your tongue ready to come out. What I did, as I've mentioned before, is I know only, kind of off the top of my head really nicely, I know sine squared plus cosine squared equals 1. I want one that involves secant, so that means I would need to divide by cosine squared. So I'm going to go ahead and do that on both sides. Of course, that's the same as dividing each individual term by cosine squared as well. So when I do, I end up getting it looks like tangent squared of theta plus 1 equals secant squared. Now that is not what I'm seeing over there in my denominator, the purple denominator, but I can make it that way if I just subtract 1 from both sides. So if I subtract 1 from both sides, that's going to give me that tangent squared is equal to secant squared minus 1. That's a big move, because that allows us to kind of move in a good direction down here. So down here, I can rewrite this expression as negative 2 in the numerator, and then all over, or divided by, our new denominator, which is going to be tangent squared of theta. And the way we do that is by using a Pythagorean identity. It's not the classic Pythagorean identity with sine squared and cosine squared, but it's a valuable set. It's a valuable Pythagorean identity nonetheless. So now that we have that, we are a step closer. I think we're almost there. And again, if tangent was your favorite trig identity, I suppose you could stop right there. But if I wanted to wrap this thing up and finish it off in probably what I'd call the best possible way, I think the way I do that is to point out that if you have the 1 over tangent squared, that's the same thing as cotangent squared. It's just a reciprocal identity. So I would instead rewrite this as negative 2 cotangent squared of theta. And I admit that's not necessarily as satisfying as anyone, but that lets us apply one more identity, in this case, as I said, a reciprocal identity. But more importantly, it gives us just a much cleaner expression than what we started with. This thing had reciprocals, the difference of two reciprocals of secant and a number, and we were able to turn it into a single trig expression. Maybe not your favorite one, but one that worked nonetheless. So I would say that would be our ultimate goal. I think negative 2 cotangent squared of theta is probably the best version of this answer, the best version of what you can simplify to. But again, your mileage may vary a little bit too. Now, what we've seen so far have been very, I'll say arithmetic. They've been very structured like fractions. In problem D, we're not looking at a problem that looks a lot like fractions anymore. Instead, what I'm seeing is kind of a structure that reminds me of a polynomial. I see cubes and squareds and all sorts of terms. There's 4 terms there. So actually, this one doesn't lead me into the same kind of arithmetic. It makes me think of more algebraic techniques. In particular, what I'm thinking is there might be some sort of factoring strategy in here. And I will admit that in years that don't feature a worldwide pandemic, you'd probably do some more intense problems involving factoring with this trig identities unit, just as kind of a review and also as just kind of a good opportunity to see what happens and see what kind of structures are out there. For now, this is probably about as hard as it's going to get. Like, this is the sort of level that we're looking at. So in here, as I look at this expression, there's a couple different ways to attack. I think an important place to start is by making a substitution, or at least thinking of it like this substitution. What I mean is this. I'm going to let there be some other variable, and I'm going to call that variable t, and I'm going to let t be equal to the sine of x. Now, it might not be immediately apparent to you why I chose to do that, but the reasoning is just simply to make that expression look more like a polynomial, like the sort of thing that we would more comfortably factor and have been factoring pretty much our entire mathematical lives for the last year or two. So if I make that substitution, especially because, remember, something like sine cubed of x is the same thing as sine of x cubed. So we talked about that with the Pythagorean identities yesterday. If that's true, it means our expression is equivalent to t cubed plus t squared minus t minus 1. So in other words, if we want to simplify this expression, before we can start applying the trig identities, we're going to need to go through and figure out how can we simplify that polynomial. Like, how can we rewrite this in a way that maybe the trig identities will clean up even further at the end? Well, when I look at this, the strategy that comes to mind is one that I was taught and called factor by grouping. In other words, what I see is I see two pairs that might potentially have some GCFs, but depending on where you learned your factoring, you might know it instead as the box. Box actually sounds kind of creepy to me when I say it, like, get in the box. But at the same time, we could do that too. So I'll demonstrate both strategies here. So if we use the box, there are 4 terms, so it's ready-made to package. It's pre-packaged like a box for this strategy. So I can pull out some GCFs, t squared minus 1. I'll pull out a t, and over here it looks like just a plus 1. So what I notice is it looks like this thing factors to t squared minus 1 times t plus 1. Now, if we were going to use the pure grouping strategy, what I would do is I'd pull out a GCF from each of those expressions. Sorry, it should be minus 1. T plus 1. I would next observe that this has a GCF of t plus 1, and I could factor that out and rewrite this expression as t plus 1 times t squared minus 1. Okay, so having done that, maybe this has helped, maybe it hasn't. Here's where we need to bring back in the trig. Like right now, we've kind of maxed out what we can simplify here. Yeah, true, we could use a difference of squares, but for the moment, we want to actually pull in the trig again. So recall, we said that t was equal to sine of x. That means this expression is equivalent to sine of x plus 1 times sine squared x minus 1. So having said that, this is where it can get a little bit challenging too, because now we have lots of choices to start to bring in. Or it might feel like we have lots of choices. Like, do we try to do something with the sine and maybe bring in a cosecant? Should we deal with the sine squared? And the answer is there's lots of different ways to get through here. My goal, though, is always to use sine and cosine where possible, just because they're the most frequent flyers. Like, we use them all the time. So what I'm going to use at this point is I'm going to use the Pythagorean identity and deal with that sine squared minus 1. So if I think about that, what do I know about Pythagorean identities? I probably know that sine squared plus cosine squared is equal to 1. So having said that, if I want to get sine squared minus 1, like I could do that, or I'll do it 2 different ways. I'll do it a different way. So if sine squared plus cosine squared equals 1, then sine squared is equal to 1 minus cosine squared. And that means that I can make a substitution right in there. So where it says, let's see if I can do this right, where it says sine of x plus 1 times sine squared of x minus 1, I'm going to make that substitution we see right over here. Sine squared of x is equal to 1 minus cosine squared. So when I bring that in, that lets me kind of see a pathway towards the ending. Now I have 1 minus 1, so those guys zero out. And instead, we're left with, it looks like, sine of x plus 1 times negative cosine squared of x. At this point, I guess my question is, does that seem like it's simple enough? And the answer is, I look at my notes and I go, yeah, it's probably fine. Like, this one was more to illustrate kind of the factoring techniques out there. The only thing I would probably tack on here is simply the fact that I would probably write it in this order, just for clarity's sake. That way there's no, ambiguity here. Was there a multiplication there or not, or was it subtraction? This is probably the best way to write that expression. But the truth is, it doesn't really go anywhere after this. In fact, in my notes from the last time I taught this in 2018, I just have a big shrug, like, they can't all be winners. Sometimes you take a bite of a Jelly Belly and it's just a bad tasting one. Like, luck of the draw. At the same time, what we got to see here were lots of good stuff. The biggest thing I'd note is that we did only apply one identity in here. It was mostly algebraic factoring. The only identity that showed up was a Pythagorean identity, and it wasn't even like a super clean Pythagorean identity either. It kind of had that negative sign left in there. So just be aware, you're not always going to get a beautiful tangent at the end. Sometimes you're just going to get something that looks a little bit like this. That brings us to example E. I think it's the second to last one. I'm 99% sure this is the second to last one we're going to look at. And as you look at it for the first time, your mind probably, immediately upon seeing it, thinks Pythagorean identity. And I don't necessarily disagree with you. It's probably a good place to go. So in fact, as you look at this, if your first instinct is to transform it into cotangent squared over cosecant of theta minus 1 by applying the Pythagorean identity up there, that's not necessarily wrong. The problem is I still don't necessarily know where to go with it. So in fact, looking at this strategy, sometimes applying the first identity that kind of catches your mind isn't actually going to resolve things for you. In fact, I'm going to erase that because I don't think it leads us in a good direction. So instead, if you don't have any path to take, a good strategy would be to go back to sines and cosines. Let's transform this into something we can work with more easily. So to do that, it's going to require a little bit of work here. Bear with me. Let's see. So, bear with me. As I say, this could get kind of grisly. So what I'm going to do is I'm first going to rewrite this cosecant squared as 1 over sine squared of theta. And of course, we still have the minus 1. And then the denominator, I'm going to rewrite this as 1 over sine minus 1. So again, at this point, I'm just trying to find ways that I can start to clean this up a little bit with sines and cosines. So in both of these expressions, my next move is going to be getting a common denominator. So in the denominator version of that 1, I'm going to multiply up and down by sine of theta to match the denominator on the left side. And in the numerator, I'm going to multiply up and down by not just sine, but sine squared of theta. So that way I can match, once again, the denominator in that portion of the expression. So when I make that switch, that's going to transform my expression. I'm going to have something all over sine of theta in the denominator. And I'm going to have something all over sine squared of theta in my numerator. What that something is, it looks like in the numerator, we're going to have 1 minus sine squared of theta. And in my denominator, it looks like I'm going to have 1 minus sine of theta. Okay, so what can we do from here? So at this point, we really have just kind of common denominator, so we've kind of sine and cosine. In fact, if I was marking this for you, I would have said we used the reciprocal identity. We used a reciprocal identity, and then down below, we used another reciprocal identity. So truthfully, a couple reciprocal identities. So from here, my next move, as I kind of look at this expression, in fact, it's so crunchy and so involved, I'm going to go ahead and copy it over, just so that way it's kind of ready to go. Oh, I can shrink this. Cool. Okay, so as I look at this expression, I'm trying to find ways that I can simplify stuff out. And, nothing's jumping out at me just yet. In fact, I'm trying to see what would be a good strategy here. Okay, let's try this. I'm going to treat this as a division problem, one fraction divided by another, and I'm going to rewrite it as 1 minus sine squared of theta divided by sine squared of theta. And then I'm going to multiply by the reciprocal, sine of theta, over 1 minus sine of theta. So in doing that, I haven't really accomplished anything, but I notice a couple things right away. First and foremost, I notice that sine of theta and sine squared of theta are going to simplify into just a single sine of theta down there in the denominator. Likewise, my numerator up there, 1 minus sine squared, I could turn that into cosine squared, but instead, because I see that 1 minus sine of theta, I'm going to instead rewrite 1 minus sine squared as a difference of squares. 1 plus sine of theta times 1 minus sine of theta. That replaces this, which means our numerator is now 1 plus sine times 1 minus sine. Down below, we have sine of theta left over, and also a factor, 1 minus sine of theta. Now, did that accomplish anything? I would argue it definitely did. take a look. We've got 1 minus sine of theta over 1 minus sine of theta. They're gone. That leaves us with the expression, which I'll write up here, leaves us with 1 plus sine of theta divided by, well, sine of theta. And although that's, I guess, preferable to what we had, I'm going to do another strategy, which isn't truly any sort of trig identity strategy, it's just kind of algebra. I'm going to separate this into 1 over sine of theta plus sine of theta over sine of theta. And the reason I'll do that is on the left, we can apply a reciprocal identity and get cosecant of theta. On the right, sine divided by sine is just 1. So rewriting it just in an order that looks more visually and aesthetically pleasing to me, we get that this expression is equal to 1 plus cosecant of theta. Now, if you're looking at that going, holy moly, that's what these are going to be like, the truth is, yeah, this could be what things are going to look like for you. Sometimes you're just going to pick a pathway, and that path is going to walk you through a whole world of thorns and twisty trees and like witches and breadcrumbs, and suddenly you're in the oven of a witch in the woods and a gingerbread. Oh wait, that's Hansel and Gretel, I'm sorry. My point is, sometimes you just pick a path and it just ends up being fairly involved. The truth is, though, in this particular expression, there was actually kind of a one-step way to do this problem that will get us to the exact same answer, of course, just far faster. That pathway involved starting at that beginning spot. So I'll copy it over just because I won't need the room, because this method would be much, much faster. If we start with cosecant squared minus 1 over cosecant of theta minus 1, you might notice that the numerator is itself a difference of squares. So I'm going to rewrite that expression, which we do have right here, cosecant squared minus 1 over cosecant minus 1. I'm going to be rewriting it as a difference of squares. Cosecant of theta plus 1 times cosecant of theta minus 1. Now when I do that, at first you might look and go like, that didn't do, oh, yeah, because you probably just saw it, didn't you? Cosecant of theta minus 1, cosecant of theta minus 1, they divide out. Our answer is cosecant of theta plus 1, also known as 1 plus cosecant of theta. So the truth is, just because you get into an expression and start simplifying and it takes you a while, doesn't necessarily mean you're doing anything wrong. Obviously, if you apply correct identities, you just might make the puzzle a little bit more complicated. It's like dumping in a bunch more jigsaw puzzle pieces from another copy of the puzzle. You might just make things overcomplicated, but theoretically you can still solve it. The truth is, though, oftentimes there is a pathway that's much cleaner and simpler. And it turns out if we had just jumped into that difference of squares at the very beginning and taking care of that numerator, we could have been done in, 2 steps? Rather than, like, this monstrosity. So again, the truth is, sometimes you're going to be frustrated because you just picked the wrong way, but that doesn't mean necessarily that there's any problem. It just means that you get to do a little bit more algebra, which for my money, I'd be perfectly happy with. If you can give me more algebra, I will take it. For you, yeah, you probably have a few more demands on your time, so maybe you prefer something different. Okay, that brings us to the final problem. Yep, the final problem that we're going to look at together for this video. We want to simplify this expression, and in looking up here at this tangent thing, there's just, again, a lot of different ways that we could go with this particular expression. So just like before, I'm going to make it my goal to show you 2 separate versions and try to see if we can find the one that kind of fits the best for you. So I'm going to speculatively place that line there and rewrite the expression on the right side. I'm not sure if that'll be enough space, but hey, we'll find out. So let's see. Let's look at this expression for a second. We have tangent plus secant times tangent minus secant. So since on the last problem, a place that we began was with a difference of squares, I think it's probably a good idea to think of this as a difference of squares. I see a plus b times a minus b. We know that should be equal to a squared minus b squared, which means this should be equal to tangent of theta squared minus secant of theta, squared, which is going to be equal to, at least a more streamlined version of that expression, it's going to be equal to tangent squared of theta minus secant squared of theta. So once again, we didn't apply any actual trig ratios yet. We just kind of did something algebraic that led us into a decent path. And you know what? I don't actually like the way that's looking, so I'm going to go ahead and move this down. I think I'll be able to make it. Okay, so there's where we stand so far. We've applied differences of squares. Now from here, as I look at this expression on this line, what my mind thinks of is it thinks of Pythagorean identities. Usually seeing those squares kind of leads us in that direction. Seeing a tangent or a sine squared makes you think of a Pythagorean identity. But in this case, we also have the pairing of tangent and secant, and I'm pretty sure those two go together. So if you'll recall the Pythagorean identities, depending on how you get there, I like it as sine squared plus cosine squared is equal to 1, and then try to construct a tangent and secant by dividing all parts by cosine squared. So if you want to, you could just do it that way and you could get to your identity. You could also do the I tan by the C I mentioned before, that mnemonic device that Miss Williams uses in her class. So in other words, you could just know right off the bat that 1 plus tangent squared is equal to secant squared. Now at this point, as I look at this expression, I've got a couple different ways to go, but what I notice is that I've already got secant squared of theta isolated in this statement of the Pythagorean identity. So I'm going to go ahead and take advantage of it. My expression that reads tangent squared of theta minus secant squared can be rewritten instead as tangent squared minus, and it says 1 plus tangent squared of theta. So having done that, I can distribute in the minus sign, and my expression will transform into tangent squared of theta minus 1 minus tangent squared of theta. And at this point, you probably see it too. Tangent squared minus tangent squared is 0, which means this identity is actually just equal to -1. It's a really complicated way to write -1, but at the same time, it is exactly equal to -1. No matter what angle you put in there, the expression will have the value of -1. So that is one potential pathway. Take advantage of the difference of square structure that's kind of lying in there, in that product that you're looking at, and then just kind of proceed through with Pythagorean identities. Now, having said that, I've mentioned that there isn't always necessarily going to be just one pathway. In fact, I would argue that there's always multiple pathways. Some are just more efficient than others. So in this case, although you probably got scared off of potentially using the break everything down into sines and cosines strategy, I actually think this one's a pretty cool one for us to use with breaking into sines and cosines. So taking that pathway for a second, think about tangent and secant. They both can be rewritten as a quotient. One is literally a reciprocal with a 1 in the top. But I'm talking too much. Tangent of theta is sine of theta over cosine of theta. And secant of theta, reciprocal identity in play, is cosine of theta. Likewise, we do the exact same thing over here, because of course these two factors have the same pieces, just a difference of a sign. So there we go. So in this case, what did I use? I applied a quotient identity twice to take care of the tangent, and then I applied the reciprocal identity to transform the secant into a cosine, or into 1 over cosine. So now having done this, what I'd point out next is the fact that both of these expressions feature the exact same denominator. So it might not have at first jumped out at you, but I noticed they both feature cosines and cosines. So I'm going to rewrite each of these into a single fraction. The first one will become sine of theta plus 1 divided by cosine of theta. And the second one, I don't even need those parentheses, excuse me. The second one will become sine of theta minus 1 divided by cosine. Now when I look at this, what I notice is now in my numerator, I've got a difference of squares again. Like nothing's really changed there. And in my denominator, I've got cosine times cosine. I can resolve that into a single expression. This will be cosine squared of theta in the denominator because we have two cosines. In my numerator, I'm going to have sine squared of theta minus 1. So now at this point, it's very tempting for people just to start canceling things out. We have to be a little bit careful here. Sine squared minus 1 isn't our traditional Pythagorean identity. Instead, we typically have like it written in a slightly different way. So I think of this as sine squared plus cosine squared is equal to 1. If we want sine squared minus 1, we can subtract 1 from both sides and subtract cosecant or cosine squared. And what we'll get is that sine squared of theta minus 1 is equal to negative cosine squared of theta. Excuse me. So with that in place, we can now substitute into our numerator. The numerator is negative cosine squared of theta from the Pythagorean identity. And yeah, it took a little bit of work, but it wasn't necessarily evil or cruel work. It was fairly straightforward. Our denominator is cosine squared of theta, and lo and behold, look what we found again. Cosine squared over cosine squared goes away, and we're left with just that -1 factor. So on the right side, of course, we get -1 as well. Now, truthfully, looking at length of work, like how much time it took, I'd say the left side's probably a little bit more efficient, but depending on your comfort with the Pythagorean identities, it might have been easier to do things on the right side and actually take advantage of that sine and cosine structure that we're just more comfortable with. Your call, totally up to you. Like, both of these methods and pathways would be perfectly valid and legal. We're definitely not going to say one is better than the other. They're just two different options to accomplish the same task. So hopefully, more than anything else, as you've watched this video, you've gotten the sense that simplifying a trig identity or a trig expression is not an exact science. There's lots of different pathways to get there, all of them equally valid, just not all of them equally efficient or time-consuming or time-intensive. So it's up to you to kind of get comfortable and start to recognize things. Doing a quick little review of what's here. When we started, we talked about just kind of basic strategies, looking for structures, trying to get things simple, like bringing a bunch of sines and cosines together, for instance, and looking for particular identity structures. Same thing with the second one. We talked about how we could see immediately something like a cofunction or an even-odd identity based on the structure of the argument. After that, we looked at a couple different pathways, things like algebraic and arithmetic things, like common denominators or splitting up a fraction into two parts or two individual fractions has been really helpful. We looked at factoring strategies and how sometimes a trig identity or a trig expression is just waiting for you to break it down algebraically into factors before you can clean it all up. And then, of course, we looked at pathways that take a long time and pathways that sometimes take a lot less. So truthfully, again, as I said, it's more of an art form than an exact science. You've just got a couple different pathways. You've got, though, a great box of tools at your disposal in those identities themselves. And it's up to you to find the pathway that best suits your understanding and what you see in that problem and leads you to a much simpler answer. So having said that, that's going to wrap up this video that went through simplifying trig expressions. Hopefully I've given you some insight about things to look for as you jump into the problem set that I'm going to go finish up in just a little bit. And hopefully it keeps you on a path and keeps you feeling comfortable with these trig expressions and working with trigonometry in ways that will definitely pay off in future courses. So thank you for watching, and have a great night.